In this portion of the module, we will introduce the concept of average rate of change. We will use it on an example from the branch of medicine called pharmacokinetics. And pharmacokinetics is a study of what's happening to a drug or medicine after it's been administered to a body. Once it gets inside a human body, the drug is being absorbed, it's being metabolized, it's being broken down to different compounds, and it will also be removed from the body for different mechanisms of expression. So pharmacokinetics considers what's happening with the drug in the body, and it is modeling these processes using mathematical equations. Pharmacokinetics is a primary approach to determine how much, how often, and for how long a particular drug needs to be taken in order to provide good results. And the discipline of pharmacokinetics uses a lot of mathematics, including integrals, limits, derivatives, differential equations, logistic equation in particular, exponential functions, and as well as probability and statistics and some approximation to it. So our example today would be a case when a certain drug is being taken through blood infusion, right? And it's being excreted through urine. So what is happening here is a patient is being monitored. All of the urine from the patient is collected, and the concentration of drug is evaluated in the urine sample. Then the concentration is multiplied by the volume of the urine sample and the amount of drug that's produced. So that's the unmetabolized drug that is being excreted from the body. So as we count those amounts of drug that are excreted from the body, we add them up. So we take, in the time intervals, everything that's leaving the body is being counted up, and we produce a table reflecting the drug leaving the body. So by 12 hours after medicine has been administered, 33.9 milligrams of the drug will leave the body. So a question may arise, how fast is the drug leaving the body? One concept that can help answer this question is the average rate of change. And here's a definition, mathematical definition of the average rate of change. Suppose we have a function that is defined on the interval, and we'll look at the change of the function over a portion of that interval from some point A to some point B. So we can define the average rate of change of the function f over the given interval AB as the following quotient. We will take the numerator, and in the numerator we'll have f of b minus f of a. That's the change in the function. And we take the denominator, and in denominator we will put change in the variable. And when we compute this fraction, we will get the average rate of change of function, apologies here, of function f of x over the interval AB. So let's go ahead and compute a average rate of change of urinary excretion of a drug as provided by this table. So here's the definition of the average rate of change right here for our use. And our exercise is to compute a few of those average rates. So here's the first question. Find the average rate of change of the function x sub u, that's the function in the table right here, on the specified interval. So the very first interval from 0 time equals 0 hours to 1 hour. So we will apply the definition here. Instead of A, we now have 0. Instead of B, we have 1. And what we have to do, we will have to evaluate function at B. We will have to evaluate function at A, and we need to divide it by the difference between B and A. That's the average rate of change. So let's see what are the values that go in there. So instead, value of the function at B is 4.0. Value of the function at A is 0. And B minus A is 1. So here we go, 4.0. Now, let's do it again. So now the same question, average rate of change, but the interval is now from 6 hours to 12 hours. So 6 is the value of A, 12 is the value of B, and we need to evaluate their formula for the average rate of change as before. And at 12 hours, the value of the function is 33.9. At 6 hours, the value of the function is 20.4. Now, B is 12 in this case, and A is 6, so denominator is 12 minus 6. So we have a fraction of, in the denominator we have 6, in the numerator we have 13.5. All right, and I will evaluate that just in a second. So in average, we can of course use a calculator to finish this computation. However, I have a different idea. I would like to bring some Google Sheets. There are so many different instruments that you guys can use to make the computations, but definitely I don't like to compute these numbers by hand. So I would like to use some technology. There's a gazillion of tools, from Desmos to MATLAB and programming languages like Python. So there are many, many different ways to do it. One of the ways to do it is to use this table. So in particular, let me just go ahead and code the formula the way we have it. So I need to take value of the function. Okay, maybe let's focus on the 6 to 12 period, right? So we need to take the value of the function at 12 hours, subtract the value of the function at 6 hours, and then divide by the difference of the value of the variable at the endpoint on the right minus the value of the variable at the endpoint on the left. So according to this, it's 2.25, which is nice. I didn't realize that's such an easy number. So let's just put it over here. Let's just record that answer over here. That's going to be 2.25. But we can also use that wonderful feature of the Google Sheets to drag the formula up and down and compute average rates of change for a whole bunch of intervals at the same time. Okay, so we will now continue with talking about instantaneous rate of change. That would be in a different segment.